Hello everyone, I'm Professor Harrison and welcome back to our module on Calculus for Finance. Today we're going to be covering functions of multiple variables and partial derivatives. We're following Victor, a fund manager whose edge is slipping and he can't figure out why, working through letters from a competitor named the Rational Quant. Today he's looking at a long-short equity book at his fund. He wants to know how the book responds to a price move in each individual name separately. By figuring this out, it's going to allow him to hedge against each individual position. He opens the latest letter from his anonymous correspondent. Up until now, every function we've worked with in this module had a single input. We had revenues as a function of price, we had bond price as a function of yield, and we had future value as a function of time. One input goes in and one output comes out. And the derivative measures how much the output responds to that single input. The trouble is that almost nothing in finance is actually a function of just one variable. A bond's price depends on the yield and the time to maturity. A portfolio's value depends on every price in it. Even the future value of a deposit depends on the principal and the rate separately. We need a tool that lets us measure how an output responds to each input on its own. That tool is the partial derivative. A partial derivative is the rate of change of a function with respect to one of its inputs, holding all the other inputs fixed. So if we have a function of x and y, the partial derivative with respect to x asks, if we nudge x by a tiny amount and leave y exactly where it already is, how does the function respond? And the partial with respect to y asks the symmetric question. How does the function respond to a tiny nudge in y holding x in place? The notation is a curly d. We write the partial derivative of f with respect to x as curly df over curly dx. That curly d, also called the partial, is the visual signal that this is a partial derivative and not an ordinary one. Alternatively, you may see some texts use a subscript instead, writing f sub x to mean the partial of f with respect to x. The two notations mean the exact same thing. Now, how do we actually compute one? It's basically as simple as it sounds. Treat every other input as a constant and apply the regular derivative rule that we already know. So the variable we are differentiating with respect to gets the standard treatment, and everything else is locked in place and treated as a fixed coefficient. Let's see this in action. Take the future value of a deposit. We have the principal P sitting in an account at rate R for a fixed term of t years. The future value is then the principal times 1 plus R raised to the t. That's the same compounding formula we've been using throughout this module. Now in this formula, P and R are both inputs. The term t we are going to just hold fixed at 5 years for this example. So we have a function of the two variables P and R. The future value is P times 1 plus R to the fifth. We'll start with the partial with respect to P. We are asking how the future value changes when we nudge the principal up by $1 with the rate held fixed. To compute it, we treat R as constant, which means 1 plus R raised to the fifth is also a constant. The function ends up looking like a constant times P. The derivative of a constant times P with respect to P is just a constant. So the partial derivative of our future value FV with respect to P is 1 plus R raised to the fifth. So what exactly does this mean? It is the per dollar growth factor. At any fixed rate and term, every additional dollar of principal that you put in ends up being worth 1 plus R to the t at maturity. Nothing about that depends on how big the principal already is, which is exactly why the derivative does not respond to the amount of the principal. Now let's calculate the partial derivative with respect to R. We hold P fixed, which keeps it out front as a constant. So we are differentiating P times 1 plus R raised to the fifth with respect to R. The chain rule from a few videos back gives us 5 times 1 plus R to the fourth times the derivative of the inside, which is just 1. So the partial of the future value with respect to R is P times 5 times 1 plus R to the fourth. So what exactly does this mean? It is the dollar response to a unit change in the rate at this principal. The bigger the principal, the bigger the response, which makes sense. A higher rate is going to compound harder when you start with a larger pile. Let's plug in numbers to see what we get. Take a principal of $10,000 at 6% for 5 years. The future value itself works out to about $13,382. The partial with respect to P, evaluated here, is 1.06 raised to the fifth, which is approximately 1.338. So at this rate, every dollar of principal grows to about $1.34 by year 5. The partial with respect to R is 10,000 times 5 times 1.06 to the fourth, which works out to approximately $100 per unit of R. The last number deserves a moment. It is a per unit of R. Since R is a rate and a unit change in R would be a 100% movement, that's not quite realistic. So to get the dollar effect of a realistic change, we can scale it. A 1% increase in R, going from 6% to 7%, increases the future value by approximately $631. A single basis point move in R is worth about $6.30 on this deposit. The partial gives us the rate per unit, and we scale by whatever change we eventually care about. So we end up with two numbers, and they're saying genuinely different things. The partial with respect to the principal tells us how much another dollar of savings is worth at this rate. The partial with respect to R tells us how much another point of yield is worth at this principal. It's the same future value, but they are measuring different sensitivities. We got both by holding one variable fixed and applying the regular derivative rules to the other. That is the whole technique of partial derivatives. Victor puts down the letter. He has a long-short equity book at his fund, and he wants to know how the book's value responds when each individual price moves, holding the other ones fixed. He now knows that's exactly what the partial derivative will give him. He is running long 50,000 shares of one position, which we'll call position A, and short 30,000 shares of another in position B. The book's value as a function of those two prices is 50,000 times the price of A minus 30,000 times the price of B. Two prices in and one book value out. So we expect two partial derivatives. He starts with the partial of the book's value with respect to the price of asset A. He treats the price of B as constant, which means the entire second term, the negative 30,000 times piece of B, is constant and drops away when he differentiates. The derivative of 50,000 times the price of A with respect to the price of A is just 50,000. So his first partial derivative is 50,000. The partial derivative with respect to the price of B follows the same logic. He treats the price of A as constant, and the first term drops away, so he ends up with negative 30,000. And here's where Victor notices something. The partial derivatives are exactly his position sizes. The 50,000 isn't a coincidence, it's the share count. The negative 30,000 is the negative of the short share count. That is why traders quote exposure in shares to begin with. The share count is the partial of the book's value with respect to the price of each asset, holding everything else fixed. He uses each partial as the dollar exposure for sizing a single name hedge against each leg. He flips to the quarterly profit and loss. His fund is finally outperforming, and he notes the improvement in the margin of his ledger. For the first time, though, he wonders exactly why the rational quant is teaching him all this. So that's the partial derivative. A function with multiple inputs has a separate rate of change with respect to each of them, and the partial derivative is the tool that picks out one input at a time and asks how much the function responds to that input alone. We compute it by holding everything else fixed and applying the same derivative rules that we already know. Two variables give us two partials, and three variables would give us three, and the technique scales as far as we need it to. These end up being the foundation for everything we'll do in the rest of this module.